For the last 40 years of his life, Albert Einstein was on a mission. He was chasing one single, monumental idea, a theory so powerful, so elegant, it could describe our entire universe with just one equation. He called it the theory of everything. Now, he never found it, but he started us on this incredible journey that's still going on today. So let's follow the breadcrumbs he left behind and explore this monumental quest to finish Einstein's dream.
You know, what was driving him wasn't just physics. It was this deep philosophical need to understand the universe at its most fundamental level. And this quote, it just nails it. The search for God equation is really about peeling back all the layers of reality to see the simple, elegant logic that's running the whole show underneath.
So right at the heart of this entire quest is a massive puzzle. You see, 20th century physics gave us these two incredible theories that explain pretty much everything we see. But, and this is a big but, they completely contradict each other. It's almost like the universe is running on two different operating systems, and they're totally incompatible.
All right, so let's meet these two pillars. They are, without a doubt, the greatest triumphs of modern science. On one hand, you've got Einstein's own masterpiece, and on the other, the strange, wonderful, and totally bizarre theory of the quantum world.
Okay, so here's the deal. On the left, you have general relativity. This is the theory for all the big stuff. Planets, stars, galaxies. It pictures the universe as this smooth, predictable fabric of spacetime that gets warped and curved by heavy objects, creating what we feel as gravity. But then on the right, you've got quantum mechanics, which runs the subatomic world. It sees the universe as this jittery, chaotic place full of tiny, discrete packets of energy, all governed by chance and probability. One is smooth and continuous, the other is chunky and random. They literally speak different mathematical languages.
Now, for most of the time, this actually isn't a problem. Physicists just use one theory for the big things and the other for the small things. But what happens when you need to use both at the same time? Well, that's when a deep crack starts to appear in our understanding of reality.
I mean, think about the very beginning of the universe, the Big Bang, or think about the very heart of a black hole. These are places that are both incredibly tiny, so you need quantum mechanics, and unbelievably massive and dense, so you need general relativity. So what happens when you force these two different rule books to work together?
A black hole singularity is really the ultimate battleground. It's a point of almost infinite density and gravity, a place where a huge amount of mass is crushed down into a tiny subatomic point. This is where both theories absolutely have to apply. And guess what? They both fail, spectacularly.
And here's how you can think about the conflict. Relativity's math is all smooth, like a ramp. Quantum theory's math is chunky, like a staircase. When you try to combine them to describe what's happening inside a black hole, the equations just completely break down. They start spitting out impossible answers, like infinity. And in physics, when your math gives you infinity as an answer, that's basically the universe's way of screaming at you, "Nope, try again. Your theory's broken." It means we need a new, deeper theory.
And this is where a truly radical idea comes into play. Back in the 1980s, a new candidate for the theory of everything emerged, and it's one that completely redefines our idea of what matter even is. It's called string theory.
You know, the core idea is actually kind of simple, but it changes everything. For centuries, we've thought of particles like electrons and quarks as these little tiny dots. String theory says, nope, that's wrong. If you could zoom in far enough on any particle, you wouldn't see a point. You'd see a tiny, vibrating loop of pure energy, a string.
And this is where it gets really beautiful. The universe is like a cosmic symphony. Think about it. Just like a single violin string can create all these different musical notes by vibrating at different frequencies, these fundamental strings create different particles. A slow vibration gives you an electron, a faster one gives you a photon, and a different kind of vibration gives you a graviton, the particle of gravity itself. All the amazing diversity of the universe, all the particles and all the forces, are just different notes being played on these tiny superstrings.
Okay, so this idea is super elegant, right? But it comes with a catch, a really, really weird one. For the math of string theory to actually work, our universe can't just have the three spatial dimensions we all know and love. It needs more.
And the math of superstring theory is very picky. It doesn't just suggest more dimensions, it demands a very specific number. For the equations to all hang together without breaking, our universe must have 10 spatial dimensions plus our one dimension of time.
Which, of course, leads to the obvious question, if these other 6 dimensions are real, where on Earth are they? Why can't we see them? Well, the answer might be that they're curled up so incredibly small that they're completely hidden from us. Let's try an analogy.
Okay, so to wrap your head around how a whole dimension can be hidden in plain sight, just picture a telephone pole way off in the distance. From far away, it just looks like a one-dimensional line, right?
But for a tiny ant crawling on that same pole, it's a different story. The ant can move up and down the pole's length, sure, but it can also walk around its circumference. That's a whole second dimension that was totally invisible to us from far away. String theory suggests our universe is just like that. The other 6 dimensions are compactified, curled up into tiny, intricate shapes at every single point in space, way too small for even an atom to notice.
So, string theory gives us this incredible picture of vibrating notes and hidden dimensions. But where does this radical idea stand today? Well, the story gets even stranger, and it's facing one giant hurdle. What's fascinating is that for a while there wasn't just one string theory, there were 5. And that was kind of a problem. But then, in 1995, physicists had a huge breakthrough. They realized that these 5 different theories were really just different ways of looking at one single deeper theory that lives in 11 dimensions. This grand unified framework is now called M-theory. The M is a bit mysterious itself. Some say it stands for magic, mystery, or more formally, membrane, because the theory also includes these other objects besides strings.
But here we are, the massive roadblock. To actually see these strings, to prove they exist, you would need an atom smasher a quadrillion times more powerful than our biggest one, the Large Hadron Collider. We simply can't generate that kind of energy. So, as beautiful as the theory is, we have 0 direct experimental proof that it's correct.
So does that just mean the theory's wrong? Well, not necessarily. As physicist Michio Kaku puts it, the problem might not be with the theory itself. M-theory is so incredibly complex that we don't have the mathematical tools yet to fully solve its equations and make precise testable predictions. It's like we've been handed the instruction manual for the universe, but we haven't learned how to read the language yet.
And this leaves us with a truly stunning thought. If our universe really is a symphony of vibrating strings, M-theory suggests there could be other symphonies out there, other universes with entirely different laws of physics. Einstein's unfinished dream might be even grander than he ever imagined. Maybe our universe isn't the only song being played, it might just be one beautiful melody in an infinite multiverse of cosmic symphonies.